So I've swapped to this style of video because editing takes too dang long, and because editing takes too dang long, I don't have time to actually do things while I'm in grad school. So if I want to make some sort of content, I might as well make it beneficial to myself and to you, primarily by trying to solve problems that I have been given in preparation for exams or for homework, and then just showing you guys a general thought process on how to handle these. I know this is a deviation from the quantum mechanics stuff that I was working on earlier on my channel. That's okay. I'll go back and I can discuss stuff like that. Also, this makes the production of videos a lot quicker, because then I can just upload this to YouTube, make a few cuts here and there, so on and so forth. The power of a whiteboard. Anyway, the textbook in particular that I'm going to be reading out of for these sets of videos is going to be Fundamentals of Statistical and Thermal Physics by F. Reif. I just can't read. And the first problem that we're going to be assessing is this one here, which is 3.4 in Reif. The problem statement itself says that we suppose that a system A is placed into thermal contact with a heat reservoir A prime, which is at an absolute temperature T prime, and that A absorbs an amount of heat Q in this process. Show that the entropy increase of A in this process satisfies this relation, delta S is equal to dQ divided by T prime. This is only valid, note, if the initial temperature of A differs infinitesimally from T prime A prime. So we're dealing essentially with a quasi-static process here, right? So we're given our systems, I already drew them here, but it always helps to add on to the picture as you work on the problem. So we know that A absorbs some amount of heat, Q. So I'm going to designate that with this arrow here. So it absorbs some amount of heat, Q, in this process. So when we do that, let's first look at the total entropy, right? We know that from the second law of thermodynamics that our total change in entropy S has to be greater than or equal to 0. So in this case, our total entropy, delta S total, is equal to our change in entropy A plus our change in entropy of A prime, and that has to be greater than or equal to 0, right? Now, our change in entropy of the reservoir A here, we can write this as an independent term, is greater than or equal to the change, or some change in heat, divided by the temperature, right? Or I'm sorry, A prime. Whoops. A prime is losing heat. So because A prime is losing heat, we can say that this is actually equal to negative dQ over T prime, right? So if this is the case, then we rewrite our equation, delta ST is equal to delta SA, and we substitute our S of A prime into the equation, minus dQ over T prime is greater than or equal to 0, and then we just have to move some terms around algebraically, which gives us that our change in entropy of our ensemble A here, whatever it might be here, just some brick, doesn't matter, is greater than or equal to some change in heat divided by the temperature T prime of our heat reservoir of A prime. And that's how I would show that the entropy increase on our side A here satisfies this relation.